I'm inviting you to back to our studio, and now our chairman of this session is coming to be with us. Please, yes, you can come here. Okay. So it will be the last session. So just only three presentations we'll have, and now I will give a floor to the chairman of the session, Dr. Viktor Skakun. So, yes.
It's a big pleasure to participate in this right now famous conference. This is the top-level conference, and I would like to launch the session B4. It's a good idea to have the program at me. So the next speaker is Valery Malyshau, nuclear detection based on single-point labels.
Hello, everyone.
Presentation.
Give me a second to start my sharing screen. Great. So my name is Valery. I'm the member of Medical Imaging Lab of the United Institute of Informatic Problems. And we developed an algorithm for nuclei detection using more easy to produce single point labels for host light images. So let's start with some general discussion. We have hematocrit and eosine images where nuclei detection often is used for classification of different types of cells that can show some malignancy in tissue. And another part of our work is immunohistochemistry, where we analyze host light images colored with specific antibody to produce a reaction in tumor cells. So cell detection here is required to identify positively and negatively reacted cells. So for our research, we have used several data sets which are publicly available, and nuclei detection often is evaluated using these data sets. Here are 4 data sets based on nuclei segmentation, and 1 which involves classification. The last one, concept data set. So for evaluation, we have tried 5-fold cross-validation to ensure stability of our results, plus fixed train test split, which was involved in these data sets where they have it. So a small review. We have classical object detection, which works with object proposals. It includes such neural networks as masker CNN, RCNN, single shot detectors, and so on. And we have nuclei detection specific neural networks, such as HARNet, which is now state-of-the-art model developed in 2018. They're usually more complicated than classical object detection, but works much better. I think 10–15% of results, if I recall correctly. So if we remember about neural network object proposals, they usually predict rectangle using one corner and height and weight. However, there are some different ways to do that in recent research, such as extreme point heat map. When we create a heat map with points in corners of objects and then create rectangles based on this heat map. Or more simple center heat map, where we want to predict centers of objects and then create rectangles using those. So what's our idea? Considering often host light image annotation for nuclei detection is performed to use it by manually segmenting every cell, and we didn't have such resources for our immunohistochemistry part, we decided to ask our partners, histopathologists, to annotate them with single points, which helps to make more data for neural networks. There were some other works which did that, but then they decided to go with some automated segmentation and predict those automatically produced segmentation. When we think that it's not eligible because we better use original data and predict the original data. And if we think what usually histopathologists require, they want some aggregated data and ability to check if it is correct. So the segmentation usually is not required by partners. More important is, for example, counting cells or percentage of cells of different classes. So our idea is to predict heat maps of nuclei centers rather than segmenting them as in classical object detection or some methods of nuclei detection. So here is our really simplified idea. We have cell, we create a smooth point and then trying to predict it. So as for our deep learning model, we were motivated by HARNet. So we used UNet-shaped neural network with residual blocks to make better propagation of signal to the end features, and then dense blocks to interpolate for heat map. Also, we have tried several losses, but MSE loss we found out that works the best. Also, there were problems with our metric calculation to compare with other work, because other work are done with object detection, so with masks, so that every nuclei is segmented. So we couldn't use general metrics for nuclei detection and object detection, such as mean intersection over union or panoptic quality. So we decided to go with detection scores for true false positives, and the main metric for us was F1 score. So here you can see the result of prediction. We've predicted the heat map of centers of nuclei and then apply a watershed algorithm to produce round shapes and make some distinction between near-located nuclei. And then if we want to produce annotation for histopathologists, we just find center of mass of every nuclei and show it to our partners. So our results on testing with HARNet, because we used some recent advances in AI, such as new optimizer, ADMP, and new activation function, we could achieve better results using HARNet itself. And then we compared it to our own model with most of training parameters locked except for the model and output data, because they predict different things. So as you can see, the results are pretty similar. They are plus minus 2%, which can be considered normal for deep learning algorithms to differ in such a way. So it can say that we can predict, we can make same prediction despite segmentation using our algorithm, using less data, which is of course faster to produce, and we all know that data is essential for deep learning techniques, and we still can get same performance. So some examples of how it looks like. We tried to add tumor segmentation to our model, and you can see the combined of different tiles, combination of different tiles. Here how looks tile predictions for Also, model works quite well to separate closely located nuclei. And then we find center of mass of every shape and combine it into AND format for histopathology software, and we can show it to doctors so they can make better diagnostic decisions. And so, thank you for your attention.
Thank you for your nice presentation. Questions? I see no questions. Please ask questions. So if not, I have one question. As far as I know, the histology images has a very high diversity, Did you try to apply your approach for different kind of histology images?
That's a great question. You're right. Okay. As I showed, there were some 5 data sets, plus we tried our model on immunohistochemistry. Give me a second. These data sets were created based on different tissues. There were two with breast cancer. We had immunohistochemistry with breast cancer. I think, if I remember right, concept data set was prostate cancer. And one of the data sets had combination of different tissues. So I think I can say that we've tried different tissues and different types of histological images.
Okay, so it works.
Yeah.
It works. Two more questions? So I see no question. So next speaker is Silun and Victor Skakun. Comparison of deep learning preprocessing algorithms of nuclear segmentation on fluorescence immunohistology images of cancer cells. Please upload your presentation and start.
Okay. Can you hear me clearly and see my sharing window?
Yes.
Okay.
Please make it on the full screen. Yes, okay.
Okay. Let's begin. Good afternoon, everyone. I'm glad to join in the conference and show you the presentation of our research. Our theme is about comparison of deep learning preprocessing algorithm of nuclei segmentation on fluorescence immunohistology images of cancer cells. Our significance of our research is that, firstly, it can raise accuracy of nuclei segmentation of fluorescence images of cancer tissue slices, and then, secondly, review the positive impact of preprocessing on segmentation. And the last one, we have compared the effectiveness of different images. Image splitting and normalization method, and then you have to choose the best one. And our research object is showed on right side. On right side is in fluorescence images, and it's about breast tumor tissue sizes. And it's stored in RGB color system. Channel red is cancer cell nucleus, and the channel green is cytoplasm of cancer cells, and the channel blue are cell nuclei. And on the bottom, it shows images in 3 channels, RGB and the masks. And on the left, it shows the area. It shows the area, histogram of area of nuclear size. We found that nuclei has the average radius in our research about 20 pixels. And then it's a pity that there are several disadvantages of the research object. Firstly, for cancer pathology analysis, our sample size are usually smaller, and it has high diversity of cancer cases, so not allowed to obtain a large number of historical images with high content quality. And secondly, experts and specialists need to manually label these images. It is a hard work for them to do. But fortunately for us, our original images, each image has hundreds of cells, so it is easy for us to splitting our image into smaller patches. So it is easier for us to increase the training set. And the last one, we all know that overtraining leads to overfitting. So increasing the training set through simply extracting with more and more overlapping will cause overfitting. And then there are two goals of our study, general goal and specific goal. The general goal, obviously, is to segment nucleus on the fluorescence images of cancer tissue slices. We used the unit structure for our research. And the specific goal of our study is to find the best way of pre-processing for our images. We separated our research into 3 steps. Firstly, define a training set of enough size. We only have 9 labeled images. So we choose 7 images for training, 1 for validation and 1 for testing. And then we tried 5 methods for extracting patches. And then 4 methods for normalization. And we have selected the neural network model, UNET. It is well known that UNET architecture is specially developed for biomedical image segmentation in 2015. UNET and its variants presently are widely used in the field of medical image segmentation. On the bottom, it's the libraries and tools we have used to build the structure of UNET. And on the right side, it is a detailed structure for our detailed structure for UNET we have used. It has a little modification on original one. So then, of course, there are many deep neuron models at the same time with UNET, such as ResidueNet, fully conventional net, SegNet, DenseNet. No, but compared the results of these networks for image segmentation, we believe that UNET is more sensitive to biomedical image, especially for segmentation. So we chose UNET for our research. And we have tried 5 methods of patching extraction. It's the first step for our research. It is to obtain a sufficiently large training set and meanwhile avoid overfitting. We have tried these cases. Simply split into patches with overlapping, and split into bigger patches with overlapping or random cropping. And the last one split into much bigger patches. And on the bottom is the result after segmentation with using method of patching extraction. We can see in the table that the fourth method obtains the better performance. It's a better result. So we chose the fourth method for the following research. Of course, we can also see the fifth method in the table, that it shows a even better result in our research. But for instance 5, although it achieves the maximum number of pixels, we in the past did an experiment based on example 2, simply increasing the training set by almost 2 times. The obtained LU metric is slightly worse. That means simply increase the training set by overlapping, by more and more overlapping is not realistic. So we chose the first method for our following research. The performance curves on the right side, we can see that it has the better performance for the fourth method. And we did a visual inspection on the segmented results. It shows on the bottom, when sufficient patches are extracted to obtain complete coverage on the image, random cropping method is more powerful. On the basis of first step, we have done second step for normalization in our research. The purpose of normalization is to limit the preprocessed data to a certain range, eliminate the negative effect that caused by singular sample data in order to improve the quality of our input data. We have tried 4 methods for our research in our research. Without normalization, deviation by maximum value, standardization, and the last one is the most useful one, histogram equalization with subsequent deviation to the maximum. Histogram equalization is to enhance the image contrast by stretching the range of pixel intensity distribution. So we chose the last one as the best one. As it shows on the right side, we can see in the graphic that the image histogram equalization, it shows better performance in the result. And in the table, we can see equalization. It got the best performance in the table, but compared with the others, it not show the obvious difference. So we thought that the image normalization doesn't play a key role in our research. So although we chose histogram equalization as the best one, but it not shows best performance. As a result, the predicted segmentation result is relatively close to the ground truth after using patch extraction and normalization, especially at the boundary. We can see in the first group of images, image, ground truth, and predict mask. We can see on the boundary, it shows nearly completely same. But unfortunately, in third group and in fourth group images, it has artifacts. And yes, it has image distortion on the boundary. So maybe in the future, in the following research, we have to add some post-processing step. So for the adherent cell nuclei, obviously, at the end, we can conclude that firstly, the random extraction of batches is more powerful, more useful. It's the best method for us to create the training set with sufficient size. And secondly, normalization can't prove that it has the active effects. That means it has no obvious effect in our research. Thirdly, through the comprehensive application of extracting patches, normalization, simple augmentation, and using a neural network model, we have got satisfied segmentation result. And meanwhile, we have avoided overfitting. That's all. Thank you all, and thank you for attention. And is there any questions?
Thank you for your presentation. Please, questions? I see no questions. No questions. So I have one question. You used the already traditional UNet model for the segmentation. Did you try your algorithm? Did you try not algorithm, but did you try the same preprocessing methods using another neural network models like UNet++ or something like that? So did you try?
Yes, I have tried several models, tried several methods. So, but we have found that the UNet, the original, also especially the original UNet structure, has obtained the best result for segmentation. The other structure of models, such as Nedzved and DenseNet, the obtained result is a little worse than UNet.
Okay, thank you. And more question?
Well, I would like to ask one question. So to continue to the question what was asked just now. You said that, so in the presentation there is that in the quite first slides, you said about that you tried to compare it with the supervised standard, ordinary segmentation algorithms. It is good that you combine these pre-processing and together with neural networks, but actually, the task you're solving is also solving by standard proprietary methods, pixel or area methods. Have you just compared these methods and the results obtained by these methods with your combination standard plus neural network? Because there are unsupervised methods which actually solving this task probably not so good, but that is a question. Have you compared?
I have compared complex network. For example, UNet has only one process as encoder. So we have built the complex structure for UNet, half using UNet and Durgoi using SegNet. And the complex structure for neural net is not shows the obviously optimization in our research. So we thought unit, the original structure unit is more useful for us in our research.
Okay, thank you.
So, thank you for your presentation. The next speaker is Alexander Leunikau, Alexander Nedzved, Alexei Belotserkovsky, and Stanislav Sholtanyuk. Sorry, multiple humans pose detection algorithms for real-time video.
Yes, hello guys, I'm here. Do you hear me?
Yes, okay.
Okay, so starting to share the screen. Okay, hello, nice to meet you. I'm grateful for the opportunity to participate in this conference. So I'll be presenting you a multi-personal detection algorithm. Wait a bit, I will hide the Zoom. Okay. So basically this algorithm, okay, let's just walk through the solutions that we have in the like current solutions, right? So basically the problem actually is to understand the human position, right? And this is a pretty old problem that was solved like years ago. And one of the classic solutions for that is like basically there are three solutions. First one is 2D solution to detect a human's pose using a predefined human model. The second one is the same one but without a predefined model. And third one is the 3D approach that uses several sources, like several cameras, to be able to understand the spatial model of the person, right? But all of them are pretty old, and the level they works is not sufficient for us. So basically, the classic mathematical methods that I used in this type of tasks are classifications using decision functions, distance functions, also clustering algorithms. Also, like nowadays, all of these kind of problems are solved by neural networks. So we're going to be focusing more on neural networks and on our approach. So basically here you can see just my friends, yeah. I was testing the algorithm on them. So as you see, we decided to go a bit further and to add some more limitations to the problem. Because we don't want to detect only one person. We would like to find a way to detect basically unlimited amount of persons, right? Of people. And we still want the algorithm to work stable, because actually when you increase the number of people, it should probably work bad. And that was the main goal for us. So as we dive deep into the problem, so basically there are three main problems with building the human virtual skeleton. So the first problem is that each image can contain the unknown number of people. And basically they can appear or disappear at any position and any point of time. And as we do the processing in real time, so basically imagine you have like, for example, 30 frames per second, and you analyze almost each frame, and each frame can, like, the amount of people can change like every second. and basically they can move and interact with each other. And so we go to the second problem, that basically the interactions between people, because interactions can cause different complex spatial interferences, occlusions. People can contact each other, and basically from the side of computer vision. So, for example, when someone touches with his hands someone's shoulder, we have to understand that there is a shoulder and there is a head, someone's head. So we have to separate these parts. And the third problem is the basically, as I said, the complexity of execution increases with the number of people. And it was basically a great restriction for the real time, as I said. So we have like a lot of frames, a lot of interactions between people, they move, and basically the amount of people can increase. Okay, so how did we solve that? The algorithm, basically the algorithm is a bottom-up method. So we estimate associations between parts, basically body parts. That means like arm, for example, leg, chest, and so on. And also we estimate the two-dimensional vector fields, which help us to encode the location of each body part. Actually, the location of each joint. Joint is, as you know, is like a moving part of the body, right? So basically, our algorithm has three main stages. Let me demonstrate them. So first of all, the first stage is preprocessing stage. We generate, like using a neural network, we generate the characteristic maps to filter areas and to narrow down the search. Because we don't want to analyze too much information, because that would be pretty slow. So then we separate to, so there are two algorithms working in parallel, because first of all, we have to detect body parts, and then we have to detect joints. And only after having body parts and joints together, we can try to measure them. And then we can try to understand which joint and which body part is like belongs to what person, right? Because like, as we know, each person has like two hands, two legs, one chest, and one head, right? So that would be a third step, is to handle multiple people. Basically, we have a huge set of body parts, and now we have to join them in a person's body, right? And make that for every person on the picture. And the final step is to build a virtual skeleton. So basically, to map all the data we have on the picture and make sure that like all the locations are positioned on their anatomical body, basically body parts, right? So basically make sure that they match. So let's walk through all these stages. So first stage is image processing. And the first stage is basically a convolution neural network with, we use the first 10 layers from the VGG19 network. And basically we generate what we do. What is the output is the characteristic maps. As I said, just to filter areas of interest. And after that, after filtering, we finish post-processing and we send these maps to our second step, which is paralleled and divided on two branches. Yeah, so as you see here, there is a like kind of interactive flow of the algorithm. So the first image is just an input, just an RGB image. Then the two next images are these parallel branches. So first branch of the neural network detects joins, basically detects the maximum points. As you see, they are red. And the second part, parallel part, is detecting basically the body parts. And then we join them together, and we are able to basically position the body part on the image. And then the next step is to understand, it is the first image, it is to understand like what part belongs to who, right? And after finishing this step, we are able to build the virtual skeleton. So let's walk through these parallel algorithms that are used to predict body parts. So first one is the simultaneous body parts detection and association. Sorry. So basically, the convolutional neural network predicts a set of probability maps, and so it is the first output of it. And the second output is a set of two-dimensional compatibility vector fields, which store the degree of compatibility between leaps. What does it mean, and how it helps us to understand? Basically, the output of this layer is the compatibility between limbs. So basically, we understand which limbs can join between each other. And we, for example, having this information, we won't join the leg with your arm, for example. Yeah, we know that the arm is joined only with the shoulder, and like that can help us basically. And okay, so the next step is to understand these body parts. All right, so to build probability maps to detect body parts. So basically what we do is we try to detect these joins, right? And our main problem is to find the peak point. So basically the most hottest point on the joint. So for example, if there is one person on the image, so there is only one peak that should be presented for each probability map, right? Because as you see here, so for example, the green one on the picture, the green circle is basically a probability map. And to be able to locate a concrete coordinate, we just detect a peak. And sometimes it could be a center. Sometimes it could be it could lay somewhere else, but like 90% of the time, basically it is a center of the probability map circle. So, and the problem is if there is more than one person, so the peak can be corresponding to like different visible parts. And that was also a difficult issue to solve. So, okay, so how do we calculate? So one of the data that we use is we use a vector field. And how do we calculate the vector field? So basically, yeah, so one of the possible ways to understand that one joint, for example, the blue point, right? How can we know that the blue point and the red point are connected, right? So basically, we add one more a middle point P, and it is a vector. So we try to understand if it lays on the in the area of the body part in the image. If it does, then we understand the direction of your body part, and we understand that blue point can match the red point, and that is done like for every body part. Next, after having all the body parts together, we have to separate them, and we have to understand which ones, which person owns which body part, right? So basically, to solve this this problem, we use graphs. Because basically it is the most convenient approach for that, because we have vectors, we know the direction, we know that every person can have only, for example, one type of body part. So using graphs, we are able to basically to separate them. And as you see on the picture 3, knowing the direction, we just know that each point, like each chest, belongs to each person, and there is no way to join them somehow else. So as for basically this was an example of processing basically one person, right? And the next issue is to process the n amount of people on the image, and we solve this problem using affine fields. So basically, when the task comes to be analyzed in a multiple amount of people, so it becomes an NP-hard task, and like with a lot of relaxations actually. So to be able to increase the efficiency, that means that we wanted to make it faster and basically to consume less execution energy. So we had to add a few optimizations. So the first optimization was to minimize the number of edges that were chosen to obtain the skeleton. So basically that was a filtering that I said before. And the second optimization was so basically the matching problem is decomposed into a set of bidirectional subtasks. Pretty difficult language, but basically this optimization means that knowing the direction of each body part and each joint, we are able to solve the issue faster, because without direction it is a very, very slow solution. So one more example of how the graph works for multiple people, multiple persons detection. So basically, first image demonstrates just the graph we have. We know that one skeleton can contain, for example, only one red, only one green, and only one blue person, right? Then we pair them. So basically, we pair all the red points together. We pair all the green and blue points together, and basically these points are the joints of the body part. So basically, every body part, for example, let's check the body part between the green and blue points, right? So basically, there are two body parts, green blue and blue red, and both of them share the blue point. So basically, in this case, we can separate the graph into two graphs, and as it is an interactive process, so by separating them step by step, we can finally get the output would be the separate parts. I think that's it. Thank you for the attention. Any questions?
Thank you for your presentation. Please, questions? So I see right now no questions. So I have one question. So you're climbing for real-time video.
Yeah.
The real-time depends on hardware. I think what kind of hardware, what kind of requirements do you have to apply for the hardware to create a real-time video for such complex processing?
Yeah, basically, we've started working on this algorithm in like I think 2 years ago, and basically the start was the AI hackathon here in Minsk, and as I had an experience in iOS development, so we decided to bring in some more limitations because we do not want to run them on servers, run the algorithm on servers or on some powerful machines. So our main limitation was to run the algorithm on board of mobile device. So basically we were testing the algorithm on 2 devices. These are iPhone 6, a pretty old device, and basically it worked pretty slow because of the hardware. But when we were started to test the iPhone X, which is pretty, I don't know, like popular device with a good GPU and CPU, the results were, so basically the results were the algorithm was working 22 FPS, frames per second, and the storage, it weighted about 28 megabytes. So that was pretty. So basically, this was aimed due to the optimizations that we did, because previously on our first stages, the algorithm was like 200 megabytes, and we were able to decrease the size almost in 10 times.
Yes, sounds promising. Yeah, thank you. More questions? We have no questions. This was the last presentation of this day. And right now I would like to announce one more conference. This conference will be held in Minsk at Faculty Radiophysics and Computer Technologies next year and end of April. End of April next year. The name, Computer Technologies and Data Processing. So please, I cordially invite you to participate in our conference. So, thank you for your attention.
Okay, thank you, the chairman. So I would like to thank you, colleague, for this nice moderation, as well as for the invitation to the conference. I think it should be spread to all the networks and to our email list and in our organizations. And by the way, do not forget to post whatever you like about the conference using hashtag in Facebook, at least hashtag PRIP, hashtag PRIP'2021, hashtag PRIP'2021 online. And well, thank you, speakers, for this nice session. What I'd like to say that we have very intensive days, so we not getting lower in our speed. So and I think tomorrow, I'm trying to announce what we'll have tomorrow. Tomorrow we'll have panel discussion. I think it will be hot and very provocative, because we'll have colleagues from different countries and from different specialities, let's say. So scientists and non-scientists, as today speaker, invited speaker said that he's not scientist from Croatia, but still he has a special opinion about AI and legacy legislation and educational problems. So the panel will start on 10 a.m. Minsk time zone, and then after the break we'll have our scientific sessions and the closing, of course. So there is everything what I'd like to say for today. Now, just enjoy your evening and see you tomorrow. Thank you. Bye-bye.
Artificial intelligence. We objectively assess the importance of this topic. However, there is still no consensus on whether all tasks can be solved using these technologies. Abuse or obligatory use. We will raise such issues of ethics, modern information society, and cybernetics. This is the story of our virtual conference on pattern recognition and information processing in 2021, which has already begun. Here, right now.